we should get started, though. All right. So I feel very fortunate to have as our visitor Simon Meierhans today. He's coming from ETH Zurich, and he's talking about some work that is really algorithmic breakthrough, and was very. He's talking about work that.
We're recorded.
Are we on? Yeah.
We're recorded.
Yeah. We're talking about work that was really a breakthrough, and there was a lot of excitement about this at. I met Simons at the Simons Institute, Theory of Computing, last fall, and there was a lot of excitement about this result because it was just emerging around that time. So look forward to hearing his talk.
Thank you. Yes, so let me get started. This talk is about almost linear time algorithms for partially dynamic graphs. If you don't know what a partially dynamic graph is, this will be defined on slide 2, so don't worry. As Phil said, I'm Simon Meierhans, and I'm a PhD student at ETH Zurich. My advisors are Rasmus King and Max Probst-Gutenberg, underlined here. And this whole talk is based on a bunch of joint works with Jan van den Brand, Li Cheng, Rasmus, Yang Liu, Max, and Sushant Sachdeva. My research is supported by the Swiss National Science Foundation and Google. So let's jump in and define what a partially dynamic graph is. So a fully dynamic graph, for the purpose of this talk, you can think of as a graph that gets both edge insertions and deletions, whereas a partially dynamic graph is one of two graphs, either an incremental graph, so a graph that only gets edge insertions, or a decremental graph, a graph that only gets edge deletions as time goes on. And in this talk, I'll talk about a few results that relate to such partially dynamic graphs. And these can be split up in two main results on graphs that undergo like edge insertions. This is the work that Phil talked about that we developed during last fall when we were at Simons. And then there's a newer work about edge deletions. And together, these yield algorithms for partially dynamic graphs. So these algorithms really form a unifying framework that allows you to solve a lot of the core questions on partially dynamic graphs via this problem called threshold min-cost flow. So threshold min-cost flow immediately gives algorithms for incremental cycle detection, bipartite matching, shortest path, min-cost flow in the partially dynamic setting, so either incremental or decremental. I'll define these applications in more detail later. So with that being said, let's learn what threshold min-cost flow is. It's maybe not too hard to glean from the name that it should be a flow problem. So you're given a graph with edge directions, so a directed graph, and a demand vector. So here it wants to send two flow from this source to this sink here that also has capacity 2. And every edge will have a capacity and a cost. And the threshold part about this problem is that we, for fixed demands, want to detect the first time a flow of cost at most f either exists or ceases to exist. And the exists part is in the incremental case where it only gets cheaper, and the ceases to exist is in the decremental case where it only gets more expensive to send a flow. Okay, and here for this small example, I will just go with f equals 5, but this is a parameter that the user of the algorithm can set. So initially, you can see that there's these two flow paths here. So this I call a flow path. And these together cost 5, where I always multiply how much flow I send on an edge with its cost. So this path costs 3 and this path costs 2. Now maybe some adversary deletes an edge. And after that, we can see that there's still a flow path from here to here that again costs 2. So I still don't have to report anything because it's still possible to send 5 flows, a cost 5 flow, sending 2 flow from source to sink. And then finally, another edge is deleted, and now it's only possible to send the demands with cost 6. So at this point, the algorithm terminates and says it's no longer possible to send the flow from S to T with cost at most 5. And the result that I talk about today is that for a partially dynamic graph, there exists an algorithm that solves the threshold min-cost flow problem in total time m, where m is the total number of edges that we see throughout the insertion or deletion sequence. We assume, furthermore, that the graph has polynomially bounded capacities and costs and that these are integral. Okay? So now that we set up this threshold min-cost flow problem, are there any questions about the definition? Good. Yeah?
So it's possible that after removing some edges, you just cannot even meet the demand vector. I guess that's in the same situation where you just report.
That's also possible, and then you also just report. That will always be possible. Okay, so then let's talk about some applications. The first application is called incremental cycle detection. Maybe some of you have heard of this. It's one of the most well-known problems on dynamic directed graphs. And the problem is just that you get edge insertions over time, and you have to report the first time a directed cycle appears. So here at this moment, there's this cycle that appears in the graph, and here we have to report the cycle and terminate. So maybe somebody in the audience already sees how this problem can be solved with threshold min-cost flow. If so, feel free to say. Otherwise, I can reveal it myself. Yeah?
Turn it into like a circulation problem?
Yeah, exactly. So you turn it into a circulation problem, which just says that like the demand that you want to ship is 0, and you give negative costs to the edges, some capacity, and set the threshold that you want to detect to something negative. And it's only possible to send a circulation around if there's a cycle. Otherwise, it would violate the constraints. But then as soon as a cycle exists, this has cost like at least -3, depends on the length of the cycle, but at least -3. So you can immediately detect the cycle once it appears by just setting the threshold to be something negative like -1. Then there's this sort of generalization of incremental cycle detection called strongly connected components. So a strongly connected component is a component of the graph in which it's possible to go from any vertex to any other vertex. And what we can also do is maintain the strongly connected components in an incremental or a decremental graph. And in an incremental graph, the first strongly connected component is sort of the cycle that appears. So it's just like running this a bit longer in some way. But in a decremental graph, it could look like this. So this is initially a strongly connected component. Then this edge gets deleted. And now we have to split it up into 2 connected components, like this strongly connected component and this, because it's no longer possible to go from here to here.
What's the output for this problem in the dynamic setting? Are you allowed to just query for a pair of edges, whether they're in the same strongly connected component or?
Here we can like just for every vertex give you an explicit number that's like an identifier of the connected component.
Good, okay.
So you can also implement and like any query that you want. Then the next application that I want to talk about is approximate ST distance. Oh, there's another question. Yeah?
Sorry, for the threshold and flow problem, I guess the question is similar to those. Are you just solving the decision problem and telling me like when the flow starts to exist or ceases to exist, or are you actually able to output the flow?
Good question. So for the purpose of this talk, you can think of it as solving the decision problem. In the incremental setting, it's easy to output the flow. In the decremental setting, we can output the flow, but we can only output it with local error. So every edge, we can say, like up to, like, let's say, a 1 plus epsilon factor, we can say how much flow there's on it. But this flow, like for the experts here, will not be demand preserving because there's local error in like how we report things. It's a noisy flow, but for these applications, this noisy flow is sufficient to extract what you need. Okay, so let's, if there's no more questions, talk about approximate ST distance. So in this problem, you're just given a vertex S and a vertex T, and you want to know what their distance is approximately as the graph undergoes either insertions or deletions. There's been a bunch of prior work on this also, and like edges might get deleted like this. And here again, like maybe somebody in the audience can immediately tell me like how I implement this using the threshold min cost flow problem. The trick is to instantiate it multiple times. Otherwise, I'll just reveal it. So you can just set the costs to be the lengths, the capacity to the all ones vector, and ask to send one flow from here to here, and then run it for a bunch of thresholds. And this will always give you an estimate that's within 1 plus epsilon of the current distance. So the total number of instances that you need to run to get this to work is like sort of order log n divided by epsilon. And then finally, there's approximate flows and bipartite matching, which is maybe the least surprising application because in the end, we are solving a flow problem. So here you can output the approximate size, let's say, of a bipartite matching in an incremental or a decremental graph. Yeah?
Why did you skip decremental cycle detection?
Oh, because decremental cycle detection, I guess, is captured by decremental strongly connected components, and it wasn't as well known of a problem, let's say. But you can also do that. Sure. Okay. So let's see what type of improvement we get. So for all these problems, we get a significant improvement over the previous algorithms that only worked for one of these. And for incremental cycle detections, strongly connected components, and approximate ST distance, we just get an improvement in the total runtime in the number of etches. And for approximate flows / bipartite matching, we get an improvement in the runtime depending on the approximation. So there's better algorithms in terms of runtime in terms of the number of etches with like some, let's say, polylog gains. But we get the better dependency on the epsilon, on like how accurate you are. So to see what such an improvement might look like, let's just look at this kind of famous problem of incremental cycle detection again. So there you see that the previous works, the previous state of the art was by Bhattacharya and Kulkarni, which sort of, if you read m as equal to n for a sparse graph, has an amortized update time of third root of n. And then there's this algorithm by Bender, Feynman, Gilbert, and Tarshan, which is super good for a graph that gets very dense when the first cycle appears, but it's not good if your graph is kind of sparse. And sometimes people ask me, well, can this even happen? Can you build a graph of size n squared that doesn't contain a cycle? And the answer is that you can. You can build the complete bipartite graph with every edge going across the direction, and then add an edge in the end. And for this instance, this algorithm is better than ours, because ours hides like some nasty subpolynomial factors in this O hat that I'll get to later. And this one has a single log n. But our algorithm is essentially linear in the number of edges for any regime, so no matter whether it's n squared or order m. If you're a practitioner, you might be complaining that this is all total update time. And this problem is really motivated by compiler design, where like if you find a cycle something has gone wrong, so you would want to backtrack. But since this is total update time, backtracking might be expensive. It might be expensive to take back an edge, because you did a lot of compute to figure out that this edge hurts. But unfortunately, it's not possible to get a worst case or like a de-amortized algorithm or a fully dynamic algorithm under common conjectures. So one of these is called the online matrix vector multiplication conjecture, and the other one is the conjecture that you shouldn't be able to detect whether a graph contains a triangle, so just like three vertices that are connected, a clique of size 3 in linear time. So if you believe that, let's say, triangle detection is not doable in linear time, then you also can't possibly de-amortize this. And the reason is that undoing stuff is really powerful. So it turns out that undoing insertions in terms of lower bounds is almost as good as being able to like fully dynamically update your graph. If you want to know more about this, you can ask me after or so. But this story is kind of a story that goes through the whole thing. So if you look at all these problems that we talked about before, like for all of these in essentially all stronger regimes, there's lower bounds that tell you that you shouldn't be able to do better. So we have this dependency amortized on 1 divided by a single epsilon, which is optimal under this online matrix vector conjecture. You should not be able to get away without approximating stuff for the ones that say approximate here. You should not be able to get away with fully dynamic, and you should not be able to get away with de-amortizing, again, under these popular conjectures in fine-grained complexity. So this is, yeah?
What exactly are the de-amortized lower bounds? Like, is it just anything sublinear is impossible under these conjectures?
No, that's not the case. Like, for example, I think triangle detection should like imply a third root of n per update. So it depends a bit on the exact lower bound, but it's like some polynomial lower bound. Think of it like third root of n-ish. Yeah, so this would be a good moment to ask questions about the results. Yeah?
But it is possible, for example, to have total update time O hat n, but each round is bounded by, let's say, square root of, depending on what this lower bound says.
This could be possible, yes. Our algorithm does not guarantee this, but this, like, you could give better guarantees on a per update level, possibly.
Repeat the question, just to...
Oh, so to repeat the question, would it be possible to guarantee something more about the worst case update time, like whatever the lower bound implies here? And the answer is that it's conceivable that you have an algorithm that has total update time O hat of n for a sparse graph, and also guarantees that each update only takes, let's say, like third root of n or something. Any more questions about the results? Then I'm excited to tell you a little bit about the algorithmic framework of like how we achieve these results. Just as a disclaimer, the 3 papers that I flashed up at the start are like 200 pages altogether, so I'm not going to go into a lot of detail for like everything. But I think I can give you a flavor of the kind of algorithms we develop, and if you're interested in the details, you should take a read. So the starting point is really this maximum flow algorithm by Chen, King, Liu, Peng, Probst, Gutenberg, and Sachdeva, which is the only algorithm for maximum flow that runs in roughly linear time. And threshold min-cost flow is in some ways strictly harder than maximum flow, so you better start with something that can solve maximum flow fast. And this algorithm takes this minimum cost flow via LP perspective. So it looks at the flow problem as a linear program, where the flow is the variable of the linear program, and the constraints just say that you shouldn't violate the capacities, you should send the demands, and then you minimize the cost. And then it takes this sort of L1 interior point method perspective. This might seem a bit daunting, but this really does like something similar to every other max flow algorithm that you might have seen before. So basically every max flow algorithm starts with a suboptimal flow. So it starts with some flow that respects the capacities, but it's not best possible. And then it tries to iteratively improve this flow. And traditionally, that was usually done by adding an augmenting path, which is just like a path that makes your flow better. And this algorithm also essentially adds an augmenting path. So every step here is a step in a L1 ball inside the polytope of flows that are feasible, and every step corresponds to applying an augmenting path. The only magic that happens via this convex optimization here is that the augmenting paths are chosen according to a potential function. So this is a potential function of the flow that tells you which augmenting path to augment along to converge quickly. And what does converging quickly mean? Here it means that you need roughly m steps. This m-step thing sounds kind of daunting because you would think that, well, you then have to solve everything very, very fast, which you do, but these boxes have kind of a large overlap in between. So you can try to exploit a dynamic algorithm or a data structure that gives you these updates faster after you've run for a few steps. So you can do this in almost constant amortized time. And this is done via a dynamic data structure that exploits that these problems locally look similar. Okay. Is the vague framework clear? Yeah?
Oh, there's a
Thumbs up. Okay, good. So let's now think about how we could dynamize this. And I'm going to be very vague here in the sense that I'll think of matching max flow and min cost flow as like roughly the same problems. It turns out that in this specific framework via these IPMs, they actually are kind of the same. So you don't get simpler algorithms if you just look at matching, let's say. So let's look at matching. And here a dynamic matching algorithm might just like match person 1 to cab 1, and then person 2 to cab 2, another one, and then an edge might arrive. And here our flow is no longer optimal, right? Like this person 3 should be matched to cab 3 and person 4 to cab 4. So here we can delete this flow or reassign person 3 to this cab and then this person to this cab. And this is sort of a general observation that we can make about the incremental setting, that the flow that we start with for the current flow remains feasible. It might just no longer be optimal. And then we can try to improve it. And in the linear programming perspective, this just corresponds to adding a coordinate to the LP. And adding a coordinate sort of relaxes the polytope, you should think. Like you can exploit that you have this extra edge. And this is exactly what's happening in the incremental setting. So you have this interior point method again, and you do steps as long as you make enough progress in the potential. And then if you can't make enough progress in the potential anymore, you just wait until the domain is relaxed or until an edge is inserted. So here maybe an edge is inserted. Unfortunately, I can only show like this in 2D, so you should think of this as like an edge get a higher capacity or so. And then you can do a bunch more steps, and this just yields you an algorithm for this threshold min-cost flow problem. Any questions up to this point? Good, then I'll continue. So the problem with this new sort of thing where you sometimes wait for the domain to be relaxed is that the dynamic algorithm of CKLPPS doesn't work against this update sequence. It only works against the update sequence that's given by MaxFlow. It sort of structurally exploits that the update sequence is nice, so it won't work if you try to use it for this problem. But we, in 2 articles that we presented at this year's talk, give a new data structure that works for every update sequence. So this gives the first half of this dynamic L1 IPM framework, where you start with a primal minimum cost flow. You do a minimum ratio cycle update, which here is phrased in this like really algebraic way, but it's really an augmenting path that you send flow along. You do this m times, and you have a lot of combinatorial structure here, and it changes really slowly. So this allows you to develop data structures that approximately preserve paths in fully dynamic graphs, and then you get like roughly m queries to these data structures. Now you might be confused why I talked about incremental as like being so important at the start, but here I'm now saying fully dynamic. Well, the reason for this is that these problems are trying to solve optimization problems inside these boxes. And it's really hard. It's really hard to relate these boxes to anything like incremental or decremental. They change slowly, but the boxes change in kind of arbitrary ways. So even if you relate the box back to a graph, it's going to be a fully dynamic graph. Any questions about the first half of the framework? Yeah?
Could you without going too much into detail, say a little bit more about what the feasible solutions within any one of these L1 boxes look like?
So the feasible solutions inside an L1 box is just you take the residual capacity on an edge and you symmetrize it by saying take the lower capacity of whichever direction you could go. And then the feasible thing is, inside an L1 box, you should just think of as you don't want to violate these capacities. And to not violate them, you just sum all of them up. And you say the sum of all of them shouldn't be larger. Or the sum of the flow change everywhere shouldn't be larger as any individual one. So if you send along a really long cycle, you make possibly a lot of loss. Because if there's a long cycle where the capacity that's remaining on every edge is 1 and the cycle has length n, my L1 box is going to tell you that you can only send 1 by n. But it turns out that this is sufficient. Sorry if you couldn't follow, this is a bit of a digression. So then let me just flash up the result. So
it turned out that, your last word, it turned out that this is not an issue?
It turns out that this is sufficient. It makes sufficient progress in the potential function that even though you're scaling your the amount that you send down by a factor n sometimes, that's fine. So this is the result that we get for incremental graphs. And now you see why I was kind of hiding this really big factor here. So this turns out to be smaller than any polynomial in M. And it's smaller than any polynomial in M because this number here is slightly less than 1. And if you think of these dynamic graph algorithms, usually whenever you add a layer of complication, you lose a factor 2 here. I know that this is not a power of 2, but you should think of it like that. So this kind of gives you an idea that our data structures are unfortunately quite layered. But all the subproblems that we solve, I would say, are quite natural. Unfortunately, I will not be able to go into the subproblems for the incremental problem here, but I'll give you a bit of a flavor for the decremental ones later, so you'll hopefully agree that the subproblems that we solve inside this huge thing are nice problems that you would want to solve anyway. So this is all I'm going to say about the edge insertion case, and the remainder of the talk is going to be about deletions. Any questions up to this point? Good. So what about restricting updates or edge deletions? We could try to run the same framework that we were running before, but here something really bad is going to happen. We're going to end up with a point outside the polytope, which just means that like our current solution is going to use an edge that got deleted. And this is really bad, because previously our algorithms were built on the idea that we always have a feasible current solution and we improve it as time goes on. But now our solution is no longer feasible. Our solution lives on a graph that no longer exists. So this seems really bad, but there's a solution. And the solution to this is just not to solve this problem, but to solve minimum cut instead. So maybe you've heard at some point that there's this duality between max flow and min cut. And if you solve minimum cut instead of maximum flow, you again have the property that a cut remains feasible. Like if I give you a current cut, this cut still exists. And if I delete edges, cuts only get better. So you can, instead of solving max flow, solve min cut and get some of the nice properties that we had in this primal case. So here we're just going to assign a probability to each vertex of being on the right-hand side of the cut. And here the probability is just like discrete, zeros here and ones here. So this would be the current cut maintained by our algorithm. And again, cuts remain feasible, and removing edges can only decrease the value. It can only make it better. So maybe this edge gets removed, and now we want to change our cut by putting this vertex on the right-hand side like this. But this cut here, although not optimal, is still a feasible cut, and the solution can only get better. So these are the two crucial things that we need. So this gives sort of the second part of the framework, where instead of primal minimum cost flow, we solve dual minimum cost flow. Don't necessarily try to parse this LP. This LP is a bit different to what I just told you because it solves minimum cost flow instead of minimum cut. But think of minimum cut for this talk. Then there's another update, but the update is not going to be an augmenting path, but sort of an augmenting cut. I'm going to talk about this in more detail later. But there's, again, a nice combinatorial structure in the update, just that this time the update is going to be a cut. And finally, we will develop data structures that approximately preserve cuts, again in fully dynamic graphs, because just like before, the box changes in arbitrary ways. And in the beginning of the talk, I said that sort of all max flow algorithms maintain a flow and augment it. I think this is the exception. This is the only algorithm that can give you a max flow that does not maintain a flow throughout the algorithm. It only solves min cut, And then in the end, you can extract the max flow from it. Okay, so again, we have to solve this m times. So m queries better be fast on average. Any questions about the general setup? Yeah?
I had some questions on the dynamic data structure. Are you going to talk more about that?
I'm going to talk about this part of the dynamic data structure. This part I'm going to leave out. Yeah?
So I think you said this earlier and I just kind of missed it. Can you say why again, like when you reduce to these combinatorial problems, then you have to solve the fully dynamic problem rather than the decremental problem?
So the reason is that the nice...
Can you repeat the question?
Okay, to repeat the question, why is the graph that we solve the combinatorial problems in fully dynamic? And the answer is that these boxes encode the parameters of the combinatorial problem, but the box changes in kind of arbitrary ways. Like, you can see that there's like large-ish overlap between the two boxes, which just corresponds to them not changing too much. But some parts of the box might get stretched, some might get smaller. We can't really control this. So this is why we have to solve a fully dynamic problem. Okay, so then let me get to what such an update in the decremental case might look like and how we extract such updates, and on the way develop the probably simplest max flow algorithm that runs in linear time. So the idea is that we want to have small steps combinatorially that go, let's say, from this cut to this cut. And how do we do that? Well, we find some augmenting cuts and add or subtract a little bit on one side of the cut. So here we add a little bit like this, and this just moves this vertex probabilistically a bit more to the right-hand side. And then maybe this happens again with this cut, but now we subtract a bit here, and then we add a bit here again, and at the end we end up with this cut. So this is what the algorithm internally will do. But the question is how to find a good cut update. And this is what this box problem refers to. But I'm going to give you a very combinatorial way of looking at this box problem now. So the IPM potential function gives you a capacity and a gradient. And these are going to be the parameters of this L1 ball update problem. And the capacity you should think of as how close are we to violating some constraint. And the gradient you should think of as just like the direction that improves. So we want to run something like gradient descent. We want to move along the direction of the gradient to improve the potential function while not violating any constraint. And now that we set up these two properties, we can talk about what this looks like combinatorially. And this again gives a graph problem where every edge is associated with two values, a gradient and a capacity. Gradients can be negative or positive. Capacities are always positive. And this is kind of similar to like the costs and capacities before, but this graph has a lot more undirected structure, which I will tell you about now. So for a given cut, we evaluate it by computing its ratio. So how do we do that? We take every edge that crosses the cut, add up the gradients and the capacities. But for the capacities, we don't care what the direction of the edge is, only for the gradient. For the gradient, we flip a sign if the edge goes against the cut. So I'll imagine this cut is like a left to right cut. So for this edge here, I need to flip the sign in front of the gradient. And this in total gives a sum of -1 for the gradients, 9 for the capacities. So the ratio of this cut is -1 by 9. And it turns out that finding a cut of minimum ratio, so as large of a number here before the minus, is going to give you a good update direction. why is this related to this problem down here? I can tell you this. You can do the algebra if you want to verify this, but basically you can square this constraint without changing it, and then one can see that after scaling, this problem is equivalent to solving this ratio problem, and then you can identify this term here as the gradient sum and this term here as the sum of the capacities, where it's relatively easy to see that a cut is an optimal solution of this problem by just scaling stuff so that the solution is between 0 and 1, and then using that one can interpret this as a probability, and if you just sample, it can't get much worse. But if you didn't follow this, it doesn't matter so much. You can show that this delta is always realized by a cut, which just sets them to 0 and 1.
And there's no is there any approximation here?
So it suffices if you solve this problem with really large error. So like basically whatever error you get in the min ratio just translates to that many extra steps in the outer algorithm. So if you get an error of 10,000 here, you run for 10,000 more steps. So this is really nice because this allows us to push some error into this problem and then just run the algorithm a bit longer. Good. So in the remainder of this talk, I'm going to tell you how we use that the capacities are undirected to build data structures that represent such cuts on undirected graphs and find such a good min ratio cut. Yeah?
I have a question which I guess I've asked at one of the flow versions of these talks, which is I guess you can unpack why this converges quickly into IPM language and why it all works out. Is there just a nice combinatorial way of thinking about improving why by update along min ratio cuts or min ratio cycles in the case of flows that the whole thing converges quickly without ever saying the word IPM? Or
I think there probably is, but I'm not currently aware of one. Okay. So my answer is ambiguous. But yeah, so to get back to the problem, we want to solve this min ratio problem. We can solve it with large approximation. How can one solve an approximation problem? One of the classic computer science tactics is to try to reduce the problem to a tree because everything is easier on a tree. So this is what we will do. We will reduce this min ratio cycle problem on this complicated looking graph to a problem on a tree. So maybe some of you have heard of Gomory-Hu trees. If not, it also doesn't matter. I'm going to butcher the definition anyway here. But a Gomory-Hu tree is sort of a weighted tree with auxiliary vertices that captures all cuts in the graph really well. So if this is the original graph, the graph that we are trying to find this good cut in, then we build a tree on top of it with these tree edges that are weighted, and this tree should capture all cuts in this graph well, which I put a bunch of algebra here, and you can have some error here. In the original Gomory-Hu tree formulation, there's no error, but I'll allow a lot of error. But what it basically says, this algebra, is that you just get a cut in the original graph. You can extend it to a tree cut, and the tree cut should be roughly the same as the original graph cut. So you have this cut in the graph, you extend it to some tree cut. This cut has roughly the same value. If this is the case for a tree, then we can show that a single edge induces a good min ratio cut. So it suffices to just disconnect every tree edge, check on which side the vertices end up, and check all these cuts, and one of them is going to be a good cut. So in the remainder of this talk, I'm going to tell you about how we construct such a fully dynamic Gomory-Hu tree. And this is what I talked about with the problems being kind of natural that we solve. I would say fully dynamic Gomory-Hu tree is a problem that would be interesting to solve anyway, because it, for example, immediately gives you approximate min cuts, approximate max flows, and like other kind of applications that you don't need the outer framework for. So this will go over expanders. I don't know who of you has seen expanders, but they are just well-linked components. And if we, for a second, assume our graph to be a unit weight like expander, there's no capacities and it is an expander, then I'm going to claim it's very easy to come up with such a tree. So an expander graph is a graph for which, for every cut, the number of edges that go across the cut is roughly proportional to the number of edges inside one of the sides of the cut. And this gives us the idea to like just cut all the edges, also the ones inside the component, which for a small example of an expander, just a complete graph on 4 vertices, would just correspond to adding an extra node and then an edge of capacity degree to this extra node. And you can see that for every cut here, the cut value over here is roughly similar. We somehow get penalized for this edge inside here a bit. We count it twice even. But if the number of edges that go out is proportional to the number of edges inside, we can afford this, at least if we're fine with paying this multiplicative loss. Okay, so for unit weight graphs, there's this nice tool called expander decomposition, which finds a lot of such clusters in the graph and guarantees that the number of edges outside the expander clusters is small. So let's see what this would look like for this graph. So it just finds this cluster, and there's only one crossing edge. And then there's this expander hierarchy due to Goranci, Rekis, Aranurak, and Tan, which just says, do what we learned about before, replace these expander components with trees, and the edges that go across, you just promote up. And then you do it again. And this time, this will be an expander, so you end up with this kind of a tree. Any questions about this setup? Good. The nice thing about this is that it's very easy to dynamize. And the reason that it's easy to dynamize is that an expander is very stable. You can't mess with an expander too much in a unit weight graph by like deleting or inserting an edge. So the authors here already made this dynamic for unit weight expanders. But crucially, if you add capacitated edges, like deleting and reinserting an edge can like really mess up your expander. It can be that a single edge has half the capacity of all the edges in the graph, and then like inserting and deleting this edge messes up your whole structure. So this does not work well for capacitated, and nobody generalized this to capacitated graphs, which we really need for it to be useful for us. So how can we get this to work for a capacitated graph? Well, we reduce to the unit capacity case, first for a graph that only gets edge deletions. And this is a standard trick in dynamic graph algorithms. You want to solve the problem for a fully dynamic graph, you first pretend there's only deletions, and then you later on with an additional layer deal with the insertions. And if there's only deletions, then this problem of like deleting and reinserting an edge of huge capacity cannot occur, because you can only delete it once. So then we can do a couple of adjustments. We can say we want to reduce the total capacity, not the number of edges. We want to just ignore edges of low capacity. So if an edge has like much less than average capacity, we're fine with promoting it, because we anyway only want to reduce the capacity between levels. So you can just ignore all edges of much below average capacity, then divide the others by the average capacity, which then gives you that the total capacity left over is roughly m. And now you just use multi-edges to represent these. And this is the whole algorithm. So for decremental graphs, this just, again, gives you such a nice tree, even if there's capacities. So the remaining challenge that I'm going to address in the last few minutes is how to deal with insertions. And for insertions, the key challenge is that given a batch of insertions, so now we will pretend that a bunch of insertions appear together, we have to process them roughly in time of the number of insertions. So no matter if I give you 1,000 insertions or 2 insertions, you have to like process it in roughly time 1,000 or 2. Okay? And once you can do that, then there's this standard tool in dynamic graph algorithms called batching that will just allow you to get a fully dynamic algorithm by grouping stuff nicely. So how could you do this? Well, the first idea is maybe to add the insertions just to the Gomory-Hu tree that we already have, and then compute another tree of that or so. But the problem is that the tree could be much larger than the number of insertions. Maybe there's only 2 insertions, but a huge tree. So here we compress the tree by making all vertices incident to insertions terminals, and then add some extra terminals such that the path between adjacent terminals are disjoint, and finally replace paths between terminals with an edge. If you didn't catch all of this, the main point is you can compress the tree part to be roughly the same size as the number of insertions. And then after this compression, we just use the algorithm that we already have for computing a Gomory-Hu tree, and then we glue these together, kind of like we take this thing here, remove some edges, and glue it together with the other thing to get a full tree back. So this, via a batching scheme, gives us a fully dynamic approximate Gomory-Hu tree. And this also gives us our ensuing algorithm for decremental graphs. And you see that here there's only a 4 divided by 3. So this is really the 2 levels that there are. There's this decremental hierarchy and then the batching scheme. So these are the 2 levels. And in total, I would say this is a very relatively neat and simple max flow algorithm. It's, I think, between 40 and 50 pages. So if you want to read about a fast max flow algorithm, you should probably start with this. So to conclude, these are, again, the results that I talked about here, where there's also some new simplification that we did. And maybe finally, in the last 2 minutes, I'll tell you a little bit about open work. So first of all, one could try to improve this almost linear to near linear time. We made some progress by like only having 3/4 there, but this seems rather tricky. Then for decremental ST shortest distance, as Alice asked at the start, it's very difficult for us to report a path. So one could try to report a path. We actually did try this for a bit. And other problems are generalizing the ST demands to single source shortest path demands, like in Dijkstra, and then also to simplify the framework even further to get practical algorithms for dynamic and static maximum flow. Thanks for listening. I didn't leave a lot of time for questions, but maybe there's a quick one.
Quick question?
Yeah.
Sorry, so did I miss something? But the algorithm for decremental graph is faster than for incremental one.
Yes.
Can you repeat the question?
So the question is the decremental algorithm faster than the incremental one? And the answer is yes.
Also, I have another question. You mentioned that undoing insertion is hard, right? But when I see, like, I don't understand correctly, but you just iteratively solve the LP. So what if you just have some persistent data structure to store all the LP solutions and undo the insertion?
So the question is why it's hard to undo stuff, given that I could just like store the stuff in a persistent data structure. I can do that, but then I did a lot of work. If I have to undo a lot of steps, 1,000 steps, then I did a lot of work, and this work I paid for by decreasing the potential. But now if you undo it, I increase the potential back up. So I can't guarantee that in the future I won't do this work again.
All right, I think we have to stop there. Thanks again.